Hi, Professor Mankowski here. In this video, we're going to go ahead and take a look at some practice exercises for hypothesis testing with population averages. And take a minute to pause the video if you like, or read through the question here on the screen. So the mayor of New York is reporting that under normal circumstances and ordinary times, if you have to go to the hospital, to the ER, and you have a non-life-threatening emergency, or rather a non-life-threatening situation, it's going to take you about 270 minutes on average to be diagnosed. Fox News Undercover comes along, and they get a lot of reports that say the average wait time is a lot higher than what the mayor says. So they randomly selected 10 patients, and they're looking at how long it took each one of them to get diagnosed. And what we have to do is we have to figure out, is the average wait time a lot higher than 270 minutes? So our job to answer that question is to figure out whatever the sample average is it significantly higher than 270 minutes? If it turns out to be that's the case, that could be kind of a bad situation for the mayor because it means that they might be making the hospitals seem a lot better than they really are. Now, if it turns out that that sample average is not significantly higher than 270, it means that the difference is just due to sampling error, and that would certainly support the mayor's comments. Now, when we read through the question, one thing that is kind of scary to us is all the information that we have to work with is going to come from a sample, meaning that we're going to have to mine all the information, the sample averages, sample standard deviation, sample size, out of the data set that they gave us. So it seems like a lot of work to do. The good news, though, is that in every question, when we do a hypothesis test for an average, we have to figure out eventually, do we do a z-test or do we do a t-test? The benefit of this problem is that decision we can make very quickly, because if we know whenever we see a data set, we're going to have to calculate the sample standard deviation ourselves, it lets us automatically know that we can go straight to a t-test. So let's start out just by writing some important information about the question. On the side, I'm going to list some of the numbers that we're going to need for the hypothesis tests. And if you're having any trouble going and calculating sample standard deviation, not a bad idea to go and review some of the earlier videos from Chapter 7 and parts of Chapter 8, where we do the walkthrough on that technique. Okay, so off to the side here, I'm going to list down some information that we're going to need. The sample size is 10. And I'm going to write down my sample average is what we have for sample average, 304.1. Our sample standard deviation (42.08). Our population average is going to be 270. And our alpha level that we've been asked to use is 0.05. And in case anybody is wondering, when we were talking about the averages, how did I know that the 270 belonged to my mu? Well, the reason I knew that was because when they're talking about an average of 270 at the onset of the question, notice how that average is not connected to the sample. So that's how I can tell if I had to choose between my X bar and my mu, I would want to go with mu for my 270. Okay, so now that we have all the important information that we're going to need, I'm going to start to set up for my HO and my H1. And we're going to follow the same pattern we ordinarily do for the null hypothesis. I'm going to go ahead and I'm going to set mu is equal to my population average of 270 minutes. For the alternative hypothesis, what are the key words that I'm going to use? Inside the question, they're talking about whether or not the wait time is much higher. And in part A, they're asking again, determine if the wait time is actually higher than what the mayor is saying. So what that tells me I need to do for H1 is going to be a right tail test. Okay, for step two, my critical values, I'm going to put in critical values for my alpha level and my degrees of freedom are what I'll need to determine the critical values. So I'm going to write alpha equals 0.05 with a right tail test, and degrees of freedom is equal to 9. And I'm going to prepare by going ahead and making a sketch here. I'm going to be on the right side, so I may as well go ahead and shade in my critical region here. And I'm going to put in critical region at alpha equals 0.05. Now, to get the actual critical value, what I'm going to have to do is I'm going to have to consult my t-tables. So I'm going to write down here critical value equals. Now I'm going to hop over to my t-tables. And first thing I'm going to do is going to take my degrees of freedom column. I'm going to drop down to where I've got 9 degrees of freedom, and I'm going to put a big underline here. Now I've got my degrees of freedom identified for my row for 9. Time now for me to go and factor in my alpha level. So I'm going to go back up to my choice of confidence interval 1 tail and 2 tail. And because I'm working with the 1 tail, I'm going to take the row for 1 tail and I'm going to move over to the column for 0.05. And my critical value is going to be 1.833. So I'm going to take 1.833. I'm going to write that down. And now I'm going to sketch that in for my critical value. Okay, so what that's telling me is eventually, when I get to my test value, I'm only going to be able to reject the null hypothesis if it turns out my sample average was more than 1.833 standard deviations away from the mean of 270. Remember, when we're doing sampling, we're assuming the null hypothesis is actually correct. And I can't really reject my null hypothesis unless I get a sample average that's so significantly different than the population average that there's a very dramatic difference. Very dramatic difference would mean my sample average would have to land in my critical region. So essentially what we're saying is I can only reject a null hypothesis if I get a sample average that I did not even have a 5% chance of getting. So let's go ahead, let's see how our formula is going to play out for step 3. I'm going to write in my formula here. And take a few minutes to calculate your formula out. Let's find out what you get. I'm going to run it on my calculator here. I'm getting 2.56. I'm going to check it twice. Exactly the same number. So now what I'm going to do is I'm going to take my 2.56 and I'm going to take a look at my curve. I'm going to see where does it fall in relation to the critical region. And it looks like my 2.56 is going to be a number that's greater than the critical value. So that's going to put me inside the rejection region. And that's all the information that I need to go ahead and carry out step 4. So for step 4, my decision rule tells me if I have sample statistic or test value that lands in the critical region, then I want to reject the null hypothesis. Otherwise, I want to accept it. Since I clearly landed inside of that critical region, I'm going to say that I will reject the null hypothesis. And for my summary step, which is really important to still remember to do, in one sentence, I can say it appears that the average wait time is actually higher than what the mayor has quoted. So now that we know all this, let's go ahead and let's take a look at question number A. Does Fox News Undercover have a case against the mayor that the average time really is higher, or was there evidence just a fluke? And our answer would be that yes, they do seem to have a case against the mayor. And for part B, describe what would constitute a type 1 error and determine what the probability of making such an error would be. A type 1 error would be if we rejected the null hypothesis and it was really true. And that would imply that when we went ahead and we took our sample, we ended up having bias in our sample, and it caused our sample average to be higher than it should have been. And that led us to do a rejection. Otherwise, we should have actually done an acceptance. The chance of making a type 1 error would have been equal to alpha, which is 0.05. So that will take care of part B. And for part C, in all cases, the sample average will be different than a population average. In Fox's case, though, was the sample average significantly different? And our answer would be, as soon as we land in the critical region, statistically, that means our average was significantly different than what the population average was. And more precisely, significantly higher. So let's go ahead, let's take a look at the next question on our practice sheet here. Pause the video if you like and read through the question. It looks like we have Cosmo Kramer, and he's running this business called the Priority Weight Loss Fitness Club. And when members sign up to join, they want to lose weight. And he's telling people that you're going to lose an average of 10 pounds a month. And there's a consumer agency that comes into the picture. They're probably there to defend customers. And they hear about his guarantee that you're going to lose 10 pounds or more the first month. So it looks like they went ahead, they sampled 36 different members. And these people in the sample, on average, they're only losing 9.2 pounds for the first month. Now, that could be really bad news for Kramer because 9.2 pounds is less than 10 pounds. So we have to decide, is his guarantee actually not valid? Like, people are paying a membership to get into his fitness center, but they're not getting what they're supposed to get. Now, on the other hand, it could be the case that 9.2 is actually within sampling error of 10 pounds, and what he's saying then would be statistically correct. So as a statistician, we have to find out which side is the right case. When we're looking at our question, we notice how, since we're doing a hypothesis test for an average, we're going to have to pay really careful attention to where our standard deviation came from. And then when we get inside the given information and we're starting to assign labels, then we're going to be able to figure out, do we have a Z distribution test or do we have a T distribution test? So we'll go ahead, we'll write down the numbers in the order as we saw them. They gave us the number 10. They gave us a 5.76. And we have 36, and we have a 9.2, and 0.01. So what's what in here? What they gave us last is probably the easiest piece because they went ahead and said use alpha equals 0.01. And also good to remember that when they give you alpha, sometimes they might refer to that as a level of significance. So we're going to go ahead, we're going to label alpha equals 0.01. For the 9.2 pounds, when they're mentioning that number here, 9.2 pounds is measured within the context of the average, an average, and they're giving that to us along with the information that occurs when they describe their sample of 36 members. Because their 9.2 is mentioned in the information about the sample, it must be the case that 9.2 is going to be, in particular, our sample average. I'm going to label 9.2 my X bar. And since we've alluded to it, the random sample then of the 36 is going to be our sample size n. The 5.76 we have to watch out for because notice how they're using the word variance when they give that to us. So that information, because it's a variance and it's coming from my population, that lets me know a couple different things. First thing I can do is I can go ahead and label this as the symbol for my population variance, but I also have to remember at this point, I need in my formula eventually a standard deviation, not a variance. So I'm going to have to make a little note on the side that says my standard deviation is going to be equal to 5.76. And this is also going to be the first spot where we get to decide. Now we're doing a z-test, because if our standard deviation is coming from the population, that lets us know we're going to be using z-curves. And the last number that we have to fill out, 10, they're mentioning in the context of the average right up here on the first line. And because that average is not connected to information about the sample, I can go ahead, I can label that my mu. So I have all the information that I'm going to need to go ahead and start to write my null and my alternative hypothesis. I'm going to get ready to construct HO and H1. My null hypothesis, I'm going to follow my same pattern I always do, mu equal to my population average of 10. For the alternative hypothesis, my key wording is they're asking me to determine if the average weight loss is actually lower. So that means they want me to test for lower. They want a left tail test. And I'm going to put in left tail test. That'll help me remember what side of the curve I need to be on. For step 2, my critical values. A couple things I need to know to get my critical values. I need to know what my sample size is. So my sample size is 10, but that's not going to be enough for my t-chart. I'm also going to have to compute my degrees of freedom. My degrees of freedom is going to be 9. My alpha level is 0.01, and I have a left tail test. So I'm going to start to do my sketch. And because I have a left tail test, my critical region is going to go on my left side here. And now I'm going to go ahead, I'm going to go into my t-tables, I'm going to retrieve my critical value that I need. Okay, so first thing I'm thinking is I'm going to go to my degrees of freedom, and I'm going to be situated on the row for 9 degrees of freedom, which I happen to be holding at. For the top three rows, confidence interval, one tail, and two tail. Since it happens to be the case that I'm working on a one tail, I'm going to be using the one tail row, and in particular, my alpha level is 0.01. So I'm going to slide all the way over to the 0.01 column, and my intercept is going to be 2.821. I'm going to write that down. And one thing we have to remember is your t values all have one thing in common. They're all positive. That's because the inventor of the t-table knew that the table was symmetrical, so they only put the positive values. If we have a left tail test, like we do now in this situation, we have to remember that we're going to take the negative of that 2.821. So I'm going to flip back over to my whiteboard view. And when I put my critical value, I have to remember to make this a negative value. So I'm going to say critical value equals a negative 2.821. And now I'm ready to proceed with step 3. So for step 3, I'm going to run my t formula. And on the denominator here, I've actually noticed a little edit that I need to make. I wrote s divided by the square root of n. This should actually be sigma over the square root of n. So not a t-test, but a z-test. I'm going to go ahead and I'm going to make that switch right now. And when I go to my formula, I have to remember that I'm switching back to the value I have for sigma. So what I need to do is remember to use the square root of 5.76. On my calculator, I'm going to find out what that number is. And that's going to be 2.4 that I need to use for my formula. Okay, sample size was given to us as 36. And pause the video for a few minutes, see if you can work out what you get for your z value. And when I compute out my z-test, I'm getting exactly -2. And I'm going to put in 0.00. So what I have to do now is I'm going to get ready to take that -2. I'm going to plot that on my curve. And it looks like that -2 is going to be about right over here. Notice how it did not make it into the critical region. So when it comes time for step 4, I apply my decision rule. The decision rule says only reject a null hypothesis if I landed in the critical region. Since that did not happen, I'm going to say I accept my null hypothesis. And now I have all the information that I need to go ahead and make my summary statement. I'm going to say that it appears the average weight loss is actually holding at 10 pounds. I'm going to go and use all that information to go ahead and take a look at part A. Determine if the average weight loss is actually lower than the Cosmo-Kramer guarantee. Based on the information I found, no, it appears that it's not actually lower than his guarantee. For part B, if Kramer's guarantee really is bogus, the consumer agency will take action. Use your answer from part A to determine if Kramer should prepare for a lawsuit. And my answer would be no, he doesn't need to prepare for a lawsuit, because what we just found was that the sample average was not significantly lower than the population average. And part C, can we attribute the lower sample average to coincidence? Our Answer would be absolutely yes, we can, because we landed in the acceptance region of our curve. That is, we did not reject the null hypothesis. So if we ended up accepting the null hypothesis, we can attribute the difference between the sample average and the population average due to merely sampling error. So we could say it was just a coincidence that the sample average was a little bit lower than the population average. Difference was nothing more than sampling error. All right, we're going to go ahead and take a look at the next question on the worksheet now. And it seems like here in this question, the setup is that the Bumblebee Tuna Fish Company, they know that if you're a person that consumes tuna, you're going to be doing about 3.2 pounds a year. And there's this executive that comes along, and the executive thinks that that mean consumption is actually inaccurate. Like maybe they think that the amount of tuna people are eating, it's trending up or it's trending down. And if you're an executive, that's really big deal to you. It's your job to be able to know if the trend for consumption is actually changing. So they go out, and it looks like they get this market research firm. The firm samples 60 different people, and it finds that those 60 people are averaging about 3.4 pounds. So our job is to figure out, is that 3.4 pounds significantly different than 3.2 pounds? And if it's significantly different, it means the company wants to start to pay attention to that, because they're probably creating products and product sizes and product packaging all to coincide roughly with a certain amount of average consumption. So this would be really important information for them. Now let's start just by taking all the numbers they reported to us in the question, writing them down. I've got a 3.2, I have a 1.13, and 60, a 3.4, and a 0.08. I'm going to start to label different things here, and the easiest one very well may be the 0.08, the last thing they reported to me, my alpha level. They said at alpha level of 0.08, and I'm going to go ahead. I'm going to fill that straight in for my alpha. Now, I noticed they're mentioning average in a couple places too. Average consumption will be 3.4 pounds. And they've also remarked that in the first line here, the mean tuna consumption is 3.2 pounds. So differentiating between those two averages, one is the sample average, one is the population average. And it looks like the 3.4 is connected to what happened in a sample of 60 people. So that's telling me my 3.4 must be my X bar. And by the process of elimination, that means that the other average, the 3.2, would have to be my mu. Okay. The sample size we drew our attention to of 60 would also be my N. And the last number I have, the 1.13, it looks like that was mentioned in the context of the population standard deviation. So not only can I go ahead and write down that this is equal to sigma, but now I know for sure I'm going to be using the Z distribution because my standard deviation came from the population. So I have virtually everything I need to go and do the remainder of the start of my hypothesis test. I'm going to write in my HO and my H1. And my null hypothesis will read just like it always does, the mu set equal to the population average that was reported to me in the question of 3.2. For the alternative hypothesis, my keywords are they believe that the tuna consumption is inaccurate. That executive thinks the tuna consumption is inaccurate, and if the executive is correct, that's alerting me to, well, inaccurate could be the population average, maybe it's supposed to be a little higher or it's supposed to be a little bit lower, but there's no direction given on whether to test for right tail or left tail. Should it be increase or decrease? Well, they probably don't know. And we almost have to imagine it for the moment as if the sample hasn't taken place yet. So if they don't know what the sample average is going to come out to be, higher or lower, I have to react by doing a two-tailed test. So I'm going to say my alternative hypothesis is going to read mu is not equal to my 3.2. And I'll write in that I have a two-tailed test. Okay, so that was step one. We're going to start to think about step two, our critical values. Now, what do I need to know for my critical values? I need to know that my alpha is equal to 0.08, and I have a two-tailed test. Okay, now why is that really important? Well, here's why I keep writing down two tails. Because at this stage, I have to take my alpha level and I need to divide it by 2. And the biggest mistake a lot of students make when they're doing the critical values is they forget to split the alpha and they end up looking the wrong value up on the z-curve. So what I'm going to do is, in big red letters, I'm going to take my alpha and I'm going to divide it by 2. And I'm going to end up with 0.08 divided by 2. So what that lets me know is when I do my curve, I have to identify the upper 4% and the lower 4% in my tails. Okay, now when I consult my z-chart, I'm going to look for the z-score that comes the closest to matching that 4%, and that number is going to be plus or minus 1.75. So what that's telling me is when I get to later stages of the question, I can only reject a null hypothesis if it turned out that the sample average was 1.75 standard deviations above the mean or more. It could also be 1.75 or more standard deviations below the mean. And now I'm going to get ready to carry out my third step, my formula. And when I calculate this out, I'm going to end up with 1.37. And I'm also going to go ahead and make one important symbol a little bit more clear to read that we wrote. This should be sigma, and it doesn't quite look like a sigma. Okay, so now that I've got my test value calculated out to be 1.37, I'm going to take a look at how that compares to my critical value. And my 1.37 does not exceed the 1.75, so that did not land me in the critical region. That means when it comes time for step 4, what I'm going to say is I'm going to apply that decision rule. If my test value landed in the critical region, reject the null hypothesis, but that didn't happen. So I'm actually going to go ahead and accept HO. And my summary would be, it appears that there's not enough evidence to reject the null hypothesis. In other words, it appears that the population average consumption is holding at 3.2 pounds. That's going to help me answer the second stage of the question right here, because they're saying, should the company make any changes in production based on the research? And our answer is going to be no, they shouldn't, because it looks like the average consumption is 3.2 pounds. And the difference that we had, we just proved, was merely owing to sampling error. Okay, we're going to go ahead with the next exercise on our sheet here. Pause the video if you need to for a minute to read through. We're finding out that the average weight of a swordfish is going to be 260 pounds. And there's this guy, Billy Tyne, and he thinks the average is too low. So he goes to do an experiment. He's going to do a sample of 85 fish, and he's going to try to show that he's correct. Now, when he does this, the big mistake a lot of people make is they'll see the words too low and they'll go ahead, they'll jump right into a left tail test. But we have to think that if he thinks the average is too low, when he does his sample, he's actually expecting it to come out to be higher. So it's going to be a right tail test. Now his sample average of 85 fish, it came out to be 265. And of course that's higher than 260, but we need to know, is it significantly higher? Because if it's significantly higher, it means that Billy Tyne is correct. But if it's not significantly higher, it means that it was just a fluke. And the difference was only due to sampling error. And by the way, Billy Tyne is actually if you're wondering where the name comes from, he was the captain of the Andrea Gale in the movie The Perfect Storm. So let's start to gear up by writing down all the numbers that they gave us. We have a 260, a 85, 265, 0.04, and 55. Okay. The first number that they gave us was 260. And the words that they use around 260 is average weight. They present average, I'm thinking of two symbols, X bar or mu. The only way I can figure out which one to use is I have to look and see where did the other average come from. And it looks like the other average is 265 pounds. And this 265 pounds appears to be connected to the information they're giving me when they're reporting the sample of what happened with 85 fish. So that's going to help me make the distinction that 265 belongs with the X bar, and 260 belongs with the mu. So my 260 is going to be mu, my 265 is going to be a sample average, X bar. And the sample of 85 is going to translate into my sample size. So I can go ahead and print up 85 is going to be my N value. And the next number that I come across is referred to as alpha level of 0.04. So I can go ahead and label my 0.04 my alpha. And the 55, they're letting me know the population standard deviation is 55 pounds. That lets me know that I'm going to label 55 my sigma. And this is also the first time I figure out that I'm doing a t-test, because population standard deviation, t-test. Sample standard population standard deviation, z-test, like Zulu, z-test. If I had a standard deviation that was coming from a sample, that would be a t-test. So I'm going to start to get ready now for my HO and my H1. My null hypothesis, I'm following my same pattern I always do. I'm going to write down mu set equal to my population average of 260 pounds. For my alternative hypothesis, I need some keywords. And we spoke about before, if he thinks the average is too low and we're trying to find out if he's correct, it's going to be the reverse. If he thinks he's underestimating something, when he does his sample, it should come out a lot higher. So that's going to be code for a right tail test. So I'm going to write in my mu should be greater than 260. with the right tail. And now I'm going to go ahead and proceed to step 2 for my critical values. I'm going to go ahead and set up a sketch. And I'm going to put my critical region on the right side because I have a right tail test. And when I consult my Z tables, I'm going to find out that my matching critical value is going to be at 1.75. So that's letting me know I can only reject the null hypothesis if the sample average I have, if my average weights of fish is more than 1.75 standard deviations from the average. It's kind of like saying we can only reject the null hypothesis if we have a sample average that we only had less than a 4% chance of getting. Remember that when we do our sample, we're assuming the population average is holding at 260 pounds. So now that I have my critical values, I can go ahead to step 3. And I can start to compute my formula. When I calculate all the numbers through my central limit theorem, I'm actually going to get a z-score of 0.83. And now my job is to take that 0.83 and compare it to the critical region. And I can see I'm not at all close to my critical region. I'm over here. I'm going to label 0.83. And that's going to give me all the information I need to go ahead and apply my decision rule in step 4. So for step 4, my decision rule, again, it says that if I do not land in the rejection region of my curve, then I cannot reject the null hypothesis. So I'm going to say that I accept HO. And my summary would be that it appears the average weight of a swordfish is holding at 260 pounds. And my sample average was a little bit higher at 265, but only due to sampling error.